Okay, today we will add another tool for the electrical and optical simulation. For this one we're going to do and add this one. This tool is used for the electrical and optical simulation. This tool is only used for the optical simulation. So here we will use this tool, and when we run the electrical and optical file, we will link this tool with the inspect file or tech-plot file or visualize to check their outputs. So first of all, we will add the S device and click OK. Now in the add file, we will use to add a command file. Click on yes. We have a command for already make a command file here. Just copy it and paste it and close it now. And yes, afterward we should add the parameter file. There are two methods to add the parameter file: by clicking on the parameter or by include the parameter file. If you click here, we have all the available option or available materials that have the parameter file. We can include like this. And the second method, we can add by clicking on the parameter. If we click on yes, it will automatically upload the silicon file. So we click it now, and we have I have already make a parameter file for the gallium antimony. So we'll just copy it and paste it here, save and close. Now here we also want to study the thickness effect, doping effect and the temperature effect of the device. So what we will do, click on the input, click on command file, and here is the command temperature. So what we will do, we just add temp. So by this method we can vary the temperature. So close it. Now what we will do, add temp, and default value is 300K. Click OK. Now next step, we will add values. The difference should be about 30, and there should be 3 values. So click OK. So we have 3 different temperatures: 300, 330 and 360. So now this is for the electrical portion. Just I explain a little about the command file. We have the file, the one in the file we have the grid file. This grid file is belong to this tool, SDE tool. As device is the parameter that we recently add, and in the output we will observe the plot file in the form of TDR dat file. We can also name it, but we have a multiple nodes, that why we are adding at the rate, so it will automatically calculate all the things. The second is electrode. If you define the work function, then it will be the Schottky one. So if we don't add anything, it will be the ohmic one. So for the ohmic contact, we have the bottom contact and the top contact. And in the parameter file, we can add the Fermi level of this metal contact according to the material that we use in the as a contact. We can also define the optical and electrical values of this electrode in the parametric file as well. The most important is the physics one. So in the physics, what we have the area factor. This area factor can be changed. By default it is 1 micrometer. If we don't define the area factor, by default is 1 micrometer. So we can also change this value. Temperature, overall device temperature. Mobility is a doping dependent, high field, high saturation, effective intrinsic density, band gap bearing by using Jane-Rawlson model. We use one website where you can find the Jane-Rawlson model for the gallium antimony. So the next thing is the recombination. SRH is both doping and temperature dependent. So for the optical simulation, recombination is important. So we check its parameters again and again. So next step is the plot one. In the plot, what we will need as in the output. So we have doping, donor, acceptor, band structures, carrier density, field and potential, current, and the generation and recombination in the output file. In the math section, we can define what we want to do. So This is the exploit error digits, no damnation is all defined. So according to the simulation requirement, we can also define some model parados and some other parameter that can also be defined in the math section for this calculation. So this is the parameter inheritance flat. This means this simulation only read those parameters that we define. For example, if we add a new material and if we don't use this command, it will, or if it will load the by default silicon parameters if we don't define this in the parametric file. So this is important. We need to define each and every parameter according to our requirement. So it will give us the output. So this is the solve. So this solve section has this Poisson electron hole. This is the condition, initial step, bottom contact we have 0.7 volt. So this is for the electrical simulation. So this is another way. There are two other way to find the overall device temperature. We can use hydrodynamic model and thermodynamic model for this purpose. And if we use the hydrodynamic, then we have defined here E temperature, and if we use thermodynamic, then we only define the temperature here. And secondly, we can add the temperature plot for the simulation, but here we don't we use the diffusion model based upon the temperature effect. So therefore we don't need an extra plot file for the temperature effect. Okay, so this portion is complete. So next, what we will do, we just pre-process node it. And run all the files. Okay, so now all the files are run. So here we can check the electrical simulation for this concentration. Take a plot. Just only open the plot file by pressing the control. Now what we apply a potential at bottom contact. So select the outer voltage bottom contact, total current bottom contact. Now here we can find the difference of temperature in the IV band. That is, if you want to check the lobe, just click on the linear lobe for along y-axis. So this is one from this one is for node 10, node 22 and 28, 100, 1, 330 and 360. So this is the difference of temperature in the electrical measurement, and after that approximately 0.5 the whole current will be saturated. Okay, the next step we will run the optical simulation. So close it. What we will do, we will add another tool as device tool for the optical one that will be shown in the next tutorial.